Welcome back to the Physics Bible. Today we're going to be looking at CP4, which is the Waves section of the Edexcel Physics GCSE. Now remember, you can do this. A good starting point for the waves topic is to actually know what waves are doing. What do they transfer? Now remember to pause the video and try and answer the questions as we go through. Check your answers with me when you unpause the video. What do waves transfer? It's as simple as that. Energy. When a wave travels, energy is being moved from one place to another. Now yes, there's lots of different types of waves. Some really obvious ones like light, which moves light energy from one place to another, such as from the sun to earth. Or sound waves, moving kinetic and sound energy from, I don't know, my voice, for example, to the microphone that's picking it up now. The two types of waves that we have to be able to describe are transverse and longitudinal. So although there are lots of types of wave that we can name, like light, sound, any part of the electromagnetic spectrum, water waves, we can categorize these into two categories. Waves that are transverse and waves that are longitudinal. So what's the difference between them? Well, let's start with transverse. A transverse wave is one that we typically think of as a wavy line. Now, the reason why we draw these waves is because we're trying to represent that as the energy moves from one point to another, particles are oscillating up and down. So think of it this way. If this was a water wave and we had a beach ball and the beach ball was in the sea and the water wave kind of travelled towards the shore, you'd often find that the beach ball won't actually come inland unless the wind's blowing or something. What you'll actually see is the beach ball just bob up and then down, and then up and then down as the wave passes through it. And the reason for this is because the water isn't actually moving towards the shore. The water is moving up and down, but it's staying in its horizontal position. So any water that goes up there isn't then going to move to the right. However, the energy of the wave does. Now that's getting into a lot of detail. Let's try and simplify it. A description for what a transverse wave is. So a transverse wave is when the vibrations or oscillations, I've put both in there because they're essentially the same thing in this example. So a vibration and an oscillation, we can use that word interchangeably. You can use either. A transverse wave is when the vibrations or oscillations are at right angles to the direction of the wave. A transverse wave is when the vibrations or oscillations are at right angles to the direction of the wave, or the direction of the way the energy is travelling. So in this example, my oscillations are up and down. However, the wave is moving to the right. So the vibrations are up and down, but the energy transfer is at 90 degrees to it. So that's a transverse wave. A longitudinal wave, however, we can use the same definition, but just tweak it slightly so that it applies to what's known as a longitudinal wave. And I'd like you to imagine that each one of these lines is a particle in the air. Without a sound wave, the particles we're going to imagine are equally spaced, they're not touching, they're not close together. When a sound wave travels, we get vibrations or oscillations that are parallel to the direction of the wave. So if we look at what's happened, so if we're going from 1 to 2, 2 is where the wave is actually travelling, and 1 is what it looks like before the wave actually moves. Think about what's happened to these particles. Some have gone that way, and some have gone that way. Some have gone that way, and some have gone that way. So instead of a vibration in the up and down direction, we've actually got a vibration in the left and right direction. So the vibrations are now that way, and the direction of travel of the wave is still that way. So compare that to before. Well, on here, a good way to remember it is that transverse begins with a T for transverse. There it is. Longitudinal waves begin with an L. Not sure if that's a little bit of a stretch as a link, but anything that helps you remember. So let's change this definition so that it actually fits longitudinal. I'm going to use blue. Stick with a colour theme. A longitudinal wave is when the vibrations or oscillations are parallel to the direction of the wave. So really, for the definition, we're only changing one specific part of it. For a transverse wave, the vibrations are at right angles to the direction of the wave, and for a longitudinal wave, the vibrations are parallel to the direction of a wave. In the exam, if you were asked about this, then you would gain credit for the diagrams. It would also help the examiner kind of understand where you're coming from, and as long as you do as I've done and label it, so this up and down, we'd write oscillations, and then this here I'd write direction of travel. And if you did that, you'd actually gain credit for the diagrams as well, so you can get marks for the diagrams. Give an example of a transverse and a longitudinal wave. So we've already mentioned a few. Can you remember which way around they are? I'd stay away from water waves if you're asked for an example, because for a transverse wave, just use any EM wave, any electromagnetic wave. So anything from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. For a longitudinal wave, the simple example is sound. So stay away from water waves as examples, because there are some very easy examples, and it's a little bit unclear what the mark scheme would be like if you said a water wave. yeah, we're still not sure what the board would say about that. So I would stick to electromagnetic waves. Next, label the wave below with the amplitude and the wavelength. So do yourself your own little diagram and then label what you think is the wavelength and what you think is the amplitude. Okay, well, the wavelength is known as the distance from one point in a wave to the same point on the next wave. So I'm going to use my red to show one wave. So an oscillation up, down and then back to the start, that is one wave. I'm now going to use green to show the start of the second wave. And that could have carried on like that. So we've actually got two waves, 1 and 2. Now, if I pick this point on the red wave, well, it's the first crest of the red wave. Where's the same point on the next wave? It's there. And so the distance from there to there, and we have to be accurate, don't just sloppily do this. Make sure you're very clear on where the arrows are touching and pointing to. Don't like do it over here or down there, because the examiner could, well, they could not give you the mark. So it's the wavelength. Now I've obviously done this by hand. Let's see how good my hand drawing has been, because if I've drawn it accurately, then the wavelength should actually be from any point on the first wave to the same point on the second wave. So what about if I choose the midpoint here? So after one up, we come back to equilibrium. There it is. Where is the same point on the next wave? See if you can put the point on. So it's after one crest, so it would be there. Now, the wavelength is about 4.1 centimeters. If I've drawn this accurately, well, I'm out by about a millimeter, just about, but you can see the wavelength is pretty much the same. And let's do it finally for the trough. If I take that to be a point, and we take that to be a point, so this is the trough of the first wave, so we need the trough of the second wave, and it should be about 4 centimeters. Yeah, might be a millimeter or so off, but it's good enough. And the symbol for wavelength is lambda, which is a Greek symbol. Next, we need to label the amplitude. The amplitude's pretty straightforward. You just have to remember that it's from the midline to a crest, or a midline to a trough. It is not the distance from the top to the bottom, okay? It's only from the midpoint to the bottom or the midpoint to the top. And I'll just put a capital A there for amplitude. And again, that distance should be the same all the way along the wave. Next, if a water wave is created and two crests reach the beach every second, what is the frequency of the wave and the period of the wave? We need to know what the definitions of these words are to answer. So the definition of frequency and the definition of period, do you know what they are? See if you can write them down, and we'll go through it in a second. So the frequency is the amount of waves per second, and the period of the wave is the time it takes for one full wave to complete its cycle. So in other words, if I was looking at a individual particle, that's going to move up and then down and then back to the middle, then the period would be the time that it takes for the particle to move up, move down, and then come back. To prove that these wave shapes are formed simply by particles moving up and down and the energy moving to the right, you can think about transverse waves like this. You can see I'm moving my pen up and down. So there's our vibration or oscillation. If I keep that movement going, but move my hand to the right, I've got to do this right, here we go, we'll see what happens. Not brilliant, but I think you get the idea. So the time period is the time that it would have taken me to go up, down and back to that point, one full wave. The same time it should have took to do that, to do that, to do that. So that there is one full oscillation. In this question, it says 2 crests reach the beach every second. So if we start the timer when this first wave goes past, so as this wave goes past, so as it travels, we start the timer, then 1 crest goes by, and then another crest goes by. That means that 2 full wave cycles have happened. So the frequency would be 2, and the unit for frequency is hertz. If it said that 2 crests reach the beach in 2 seconds, then what would the frequency be? Well, if 2 reach in 2 seconds, that means that's 1 per second, and so the frequency would be 1 hertz. If there was 100 waves per second, then that would be 100 hertz. To get the period, the equation for the time period is 1 divided by the frequency. Obviously, if 2 are happening per second, then it means that it must be half a second each. And we can prove that by putting in the number for frequency, which was 2. And so the final answer is 0.5 seconds, or half a second. If the frequency was 10 hertz, what would the time period of the waves be? Well, you would just put the 10 hertz into the frequency bit. It would be 1 divided by 10, which would mean 0.1 seconds, which makes sense if you think about it. If it takes half a second for a full oscillation, then you're going to fit 2 in 1 second. But if it only takes 0.1 seconds, then you're going to get a full oscillation 10 times a second, because it only takes 0.1 seconds to do 1 oscillation. Next question. Name a type of wave that doesn't need a medium to travel. Do we know what the word medium means? It's another way of saying substance. Usually made of particles. So air is a medium, light is a medium, even glass is a medium, or even wood is a medium. Something that particles vibrate or oscillate or move around when a wave travels through them. So what doesn't need a medium? It's the same answer to this question. Any EM wave. Because electromagnetic waves don't need particles to travel. Which is a good thing, otherwise we would be able to get no light or heat from the sun. Instead, EM waves don't need particles, and so they're able to travel through space from the Sun to the Earth, and the energy can be delivered to Earth. We're now going to be looking at the speed equation, which is speed equals distance divided by time, or S equals d over t. Now, we've already seen this equation before when dealing with motion, but we can use this equation in a wave question if we know the distance that the wave travels and the time it takes for the wave to travel that distance. The other equation we may use in this section is velocity equals frequency times wavelength, or V equals F times lambda. Which one to use will be based upon what information you're given in the question. So let's just dive right in with the first question. Calculate the speed of light which travels 900 million meters in 3 seconds. So do we have a frequency? No. Or a wavelength? No. But we do have a distance and we do have a time. So speed equals distance over time. The speed is therefore the distance of 900 million divided by, and the time it took was 3 seconds. So our final answer for the speed would be 300 million meters per second, which is actually the speed of light. You hear thunder 5 seconds after you see the lightning. How far away is the lightning strike? I'm actually going to jump straight to this question before we go back to this, because we have to make an assumption to answer this question fairly. And the assumption we're going to have to make is that the light arrives instantly. That's the assumption we're going to make. So we hear thunder, which is the roaring sound, 5 seconds after we see the lightning strike. So the assumption we're making is that the lightning strike and the light arriving from it is instantly reaching us. And then obviously we start the timer and 5 seconds later we hear the thunder. In reality, it will take a small amount of time for the light to arrive from the lightning to our eyes. But because light travels at 300 million meters per second, and the speed of sound is 330 meters per second, then light's approximately 1,000,000 times faster than sound. So we're going to assume the light arrives instantly. So we've been given a time and we're asked to calculate how far away the lightning strike is. Well, that's a distance, and we know the speed of sound is 330 meters per second, so we've got S. So we've got S, we've got T, and what we need to find is D. We go back to this equation and yep, it's that time again. We're going to have to rearrange it. So how do you rearrange this equation to get D equals? Have a go yourself. So the distance equals the T gets moved to the other side and next to the S, so it's speed times time. So the distance that the sound has travelled is 330 meters per second, and so if it travels for 5 seconds, then remember not to take any risks. 330 times 5, 1,650 meters. What's that in kilometres? To turn it into kilometres, we would just divide by 1,000. 1, 2, 3. 1.65 kilometres or kilometres. The next question involves Mr. Percy being immature by the looks of things. Mr. Percy bombs into a pool and creates water waves. The waves have a wavelength of 6 meters and a frequency of 0.5 hertz. Calculate their speed. Well, in this example, I don't see anything about the distance, although this is measured in meters, but it's actually a wavelength. So instead of this equation, we're going to use this. Let's label our numbers. So that is wavelength, so I'm going to put the wavelength symbol next to it. And we've been given frequency, which is f. And we have to calculate the speed, s. Now s is for speed, but in this equation we're actually going to use the term velocity. In this case, and in this topic, speed and velocity, you can treat them as exactly the same thing. They're both measured in meters per second. Yes, we know now that velocity includes a direction, but this question doesn't make direction an important point at all. So it doesn't matter what direction the wave's travelling in. So speed and velocity are the same thing. So we've got v, f, and lambda. What's my frequency? 0.5. What's my wavelength? 6 meters. And so the final answer is 3 meters per second. Let's try using that equation again, but we're going to have to rearrange the equation. See if you can do this one on your own. Sound travels at 330 meters per second, and a sound is heard at a pitch of 110 hertz. What is the wavelength of the sound? Hopefully you've done this yourself by now. One thing that might have thrown you is that the sound is heard at a pitch of 110 hertz. Now, pitch is just another word for frequency when talking about a sound wave. So the higher the frequency, the higher the pitch, the higher the note of the sound. So we've been given frequency, we've also been given the speed of the wave, v, but it's asking us to work out the wavelength. Looking back at our equation, we need to rearrange it to get lambda equals. This should be obvious by now. We need to get rid of the f. Because they're multiplied, the f gets moved to the other side of equal sign and it goes underneath the v. So lambda equals v divided by f. And then we just put our numbers in. 330 divided by 110. Final answer is 3 meters. Complete the following wave/ray diagrams. We've got some glass, so the area above the black line is meant to be the medium of glass, here, here and here, and below the line is air. So essentially in this first diagram we've got a ray of light that's going into it could be a glass block, it could be a glass window. What's this effect known as? This part of the wave syllabus is looking at something called refraction. And refraction is when a wave changes direction when it changes speed. Now, just like us, if we were running and we entered into something which was more dense, so for example, trying to run through water, you'd actually run a lot slower. Waves experience the same thing. When they go into something that's more dense, they travel slower. Glass is more dense than air. You can go through this in your revision guide, and there's analogies about the wave going into mud or into sand, but really we can just learn which way the light turns when it changes speed. And if light slows down, so if it goes from air into glass, it always turns towards this line. Now this dotted line doesn't really exist. It's just to help us do the diagram, and it's got a name beginning with N. Hopefully you know that that's known as the normal line. So let's think about where the light ray would go if the glass wasn't even there, if it just carried on, and it would do that. Okay, it would go in a straight line. But because of the glass, the wave is going to change direction. It's going to turn towards the normal, and so instead of it being up there, we're going to have to make it go towards the normal, which means it gets turned like that. So our final answer would be that red line there. Turns towards the normal. What about if it hits straight on? Well, we can't see it, but if we were to draw the normal, I should have used a ruler there. That's me being bad. You should always use a ruler when doing ray diagrams. This time, because the light ray is coming in at right angles to the glass, then it can't bend towards or away from the normal, because it is actually travelling along the normal. In this scenario, the answer is that the wave will actually just carry on in a straight line, like that. And here, we're going from glass into air. Now if you draw that yourself, and see if you can complete it. Pay attention to the direction of the wave. We're going from glass into air. Hopefully you remembered to draw the normal. The normal is always at right angles to the boundary. The boundary is where the glass and air meet, so that line's the boundary. We've drawn the normal at right angles to the boundary. Let's think about where the light would have gone if there was no change in medium. Well, it would have gone this way. It would have gone over there. But because it's going from glass into air, air is less dense, so the wave is going to speed up. And instead of moving towards the normal, this time it's going to move away from the normal. So our final answer will look like that. If you think about this wave being reversed, so let's say it was a ray of light travelling through the glass and it reaches the boundary, through the air and it reaches the boundary, then what would it do? Well, it would have gone over there, but when it goes into the glass it would slow down and move towards the normal. So you can see that it works both ways. In the next video we're going to be looking at CP5, which is all about light and the electromagnetic spectrum. Hope to see you there, and I hope you found this useful.